Now we're going to talk about how to do an experiment on friction to figure out what the coefficient of friction is. There are two good ways to do this. One is to take a piece of your track, not the actual track, but just a piece of whatever kind of tube you're using, clear or foamy tubes, and set it up at an angle. You don't need to measure the angle. You can measure the height and the length of the track, and then the sine of that angle is equal to the opposite over the hypotenuse. So in this case, to get the angle, I would do sine minus 1 of h over L. You need these measurements anyway, but you need to figure out what the angle is. Then take your marble, drop it down the track, and I would suggest using video physics to figure out what the time is, or taking a lot of time runs so that you can minimize your error. But you want to get a time for the marble to go down your track. So you're going to end up with sort of a data point, which is the time for this. It's gone a distance in a time. We know it's had an acceleration. It started at a 0 velocity and it got faster and faster. We want to find that acceleration because finding that acceleration will help us find the force of friction. The equation for that is that distance equals the initial velocity times time plus 1/2 the acceleration times time squared. Since my initial velocity was 0, that makes that very easy. My distance was L, the length of the track. That's going to equal 1/2 the acceleration times the time I got squared. I'm going to solve this equation for the acceleration because I'm interested in the acceleration. So that's going to be 2L over t squared. And whatever that number is, I want that number. I'm going to then think about the force diagram involved of my marble when it's on the track. I've got the weight. Obviously this track is still at an angle. That weight is going to break into two components. One of those components is going to equal the normal force. I don't really care about that component. The other component I care about, that's the downhill component. If this angle is, say, 30 degrees, that means this angle will be 60 degrees, and this angle will be that original 30-degree angle that I calculated. You might not have 30 degrees. It's whatever your angle is. So this down the hill piece is the weight, mg, times the sine of that angle. So that's one of the forces. Another force, obviously, is the force of friction. And my net force in the downhill direction is just going to be this mg sine theta, the component of the weight downhill, minus the force of friction. And this net force is going to equal the mass times the downhill acceleration. Now, you calculated the downhill acceleration. It was 2L over t squared. So that's great. The other thing is that the force of friction is equal to the coefficient of friction times the normal force. And in this case, the normal force is going to be equal to that other component of the force of weight, the gravity. So this component is mg cosine theta, which means that the normal force is equal to mg cosine theta. And the force of friction here, I can rewrite as the coefficient times mg cosine theta. So my whole thing, I've got mass times downhill acceleration, which is 2L over the time you measured squared. And that's going to equal mg sine theta minus mu mg cosine theta. The really nice thing here is that all the masses cancel. And you're going to solve this equation for mu. You're trying to get the coefficient of friction with this particular experiment. Once you have the coefficient of friction, you can always find the friction based on the normal force. So on all of your force diagrams now, once you've calculated the normal force, you can use your experimentally and mathematically derived coefficient of friction to help you find a perfect number for the force of friction, and that's a way to get extra points for friction. That's one of the two experiments you can do.